Back to C439. In this video, you will learn the second part of this chapter, which is about finishing work. First, let's distinguish between grading and finishing. These two activities follows excavation and compaction to level an area to a desired shape and elevation. While grading is the process of roughly leveling an area, finish grading, or simply finishing, is the process of smoothing earthwork at a higher level of accuracy. Finishing will prepare the final surface to the desired shape and elevation required by the plans and specification. It is done after rough grading. The machine shown in this figure is called motor grader. It is most widely used for grading and finishing. A smooth surface is typically the result of grading and finishing process. The final surface can have a flat shape like this. In many cases, you will need to cut ditches at the edges. Also, the elevation at the center line may be lowered down or raised up compared to the edges. Here are 3 learning objectives. Number 1, ability to estimate motor grader speed based on operational task. Number 2, ability to estimate motor grader production. Number 3, understanding of equipment used for finish grading. Here is a picture of motor graders in the old day. This grader was built in 1919 by the Russell Grader Manufacturing Company. This was a newer grader. It was produced by Caterpillar in 1928. Here are examples of modern motor graders. Section 1. General information on motor graders. Please see pages 87-89 in the textbook for more details. First, we use motor graders for what purposes? Motor graders are multi-purpose machines, which can be used for planning surfaces, such as heavy blading, side preparation, grading, and finishing. Blading is the process of removing the top material of an area. It is done by dragging the blade on the surface when the machine is moving forward. Typically, the blade is positioned at the 45-degree angle. This is to move material to the side of the machine. Motor graders are also widely used for site preparation, such as spreading the dumped soil. As discussed earlier, at the beginning of this video, grading is the main application of motor graders. Finish grading, or finishing, is another main purpose of this machine. It is used to make the final shape and elevation of the area. In addition to preparing surfaces, this machine is used for cutting and cleaning ditches. This picture is showing a grader used for cutting the ditch. For many cases, cleaning vegetable or grasses is required before cutting the ditches. The grader can also be used for this purpose. Graders are also used for slope work. This picture shows a grader in operation to make the final surface of the slope. The vertical angle between the blade and the ground can be adjusted up to 90 degrees. Furthermore, motor graders are commonly used for maintenance of unpaved roads or haul roads. After years in operation, unpaved roads, such as dirt or gravel, deteriorate quickly. The problems include the existence of rutting and potholes, or no crown. Graders can be used to bring the road surface to its original shape and crown. Roads that are used for hauling material also need regular maintenance. Especially for heavy-duty haul roads, problems develop quickly and would impose further resistance on the haul units. Therefore, it needs to be regularly regraded. Graders are also used a lot for moving or spreading material. This picture shows a grading being used for moving windroad material. This is the top view of a grader when being used for moving windroad material. As it goes forward, the blade spreads out the material line underneath. It is also used for spreading dumped materials. When spreading dumped material, the machine travels along beside the material. Two parts of it are not in a straight position. The front part is typically arranged at an angle of 15 to 18 degrees to the moving direction. Finally, we can use grader for snow removal. It is used to quickly clean off the snow from the roadway. Next, let's learn about the main components of a grader. Moldboard, which is commonly referred to as the blade. It is a working part of the grader, which being considered as the one that characterizes the unique operational functions of the grader. The angle of the blade can be adjusted to achieve numerous positions. It can be parallel or even perpendicular to the ground. This is a side view, and here is a planned top view of the blade. The blade can rotate around the vertical axis at the joint so that it can move material from either side of the machine. The vertical angle of the blade to the ground is called pitch. This measure depends upon the cutting application. For light cuts, you set a small pitch. When you need a maximum cut, it should be in the completely vertical straight position. Another key component of the grader is the scarifier. A scarifier is attached in front of the machine. It can be used to break up material, which is too hard to cut with the moldboard. A scarifier can also be located in the middle, between front tires and the blade. When need to break hard soil, it is lowered to the ground like this. Graders can also be equipped with a rear ripper to achieve greater depths, especially for breaking extremely hard soil and rock. For such material, the scarifier may not be strong enough to cut. Ripping is typically applied before grading. Ripping helps to soften the soil, which is then moved using the blade. Let's watch a short video of some graders in operation. Section 2. Estimating grader production. You can read this part in page 90 in the text. The grader production is mainly determined by the speed of the grader. The faster the machine can travel, the more soil it can produce in each hour. Speed is the most difficult factor to estimate in advance, and speed estimates may need to be adjusted based on the field experience during construction as the work progresses. You can use Table 5.6, page 90 in the textbook, to find typical grader operating speeds. In addition, the Caterpillar Performance Handbook 47, page 1127, provides typical speeds for various grader operations. This is Table 5.6 in your textbook. Given an operation application, such as sloping or finishing, you can quickly find the corresponding speed. It won't give you an exact number, but it typically gives you a range between a low and high speed. This is another source of grader speeds. This table is from Caterpillar Performance Handbook, page 1127. It also gives you a speed range for various applications. We will have an example in the later part of this video, in which I will show you how to use the handbook to find speeds. When designing a grading operation, it is useful to calculate the total time required for a grader operation. To calculate total time, you can use equation 5.2 in your textbook, as shown here. In this equation, T is the time, in hours. P is the number of passes required. D is the distance traveled, in miles or feet. S is the speed of grader, in miles per hour or feet per minute. Remember that 1 mile per hour equals 88 feet per minute. Finally, E is the grader efficiency factor. The total time is equal the number of passes times the distance divided by the speed and efficiency factor. Now, let's apply that equation to solve this example. A CAT140M motor grader is performing maintenance on 3 miles of an unpaved road surface. The operation will require 2 passes in second gear and 3 passes in fourth gear. Due to the long passes in road maintenance, which resulting in fewer turnarounds, a job efficiency of 0.80 will be used. You are required to determine the total time required to complete the work. This is a given table, which provides the speed of the 140M model. You can see this table in Caterpillar Performance Handbook 47, page 1119. Note that, during grading, the grader makes forward movement. You only need the forward speed when estimating grader production. Remember, in this example, the grader is required to make 2 passes in the second gear and 3 passes in the 4th gear. So you need to find the forward speed at the 2nd and the 4th gears. From this table, you got 3.4 miles per hour and 6.9 miles per hour respectively for gear 2 and 4. Now, you can apply equation 5.2 to estimate the total time. Remember, the machine operates at 3.4 miles per hour in the first 2 passes and 6.9 miles per hour for the last 3 passes. So you need to calculate 2 separate time components. First, the total time for the first 2 passes. It is equal to 2 passes multiplied by 3 miles per pass divided by the speed of 3.4 miles per hour and the efficiency of 80%. Then, you need to add it with the total time during the last 3 passes, which is equal 3 passes times 3 miles per pass divided by 6.9 miles per hour and 80% efficiency. The result is 3.84 hours. Let's do another example. In this example, the same CAT140M motor grader is used to clean ditches on a 2,000-foot stretch of road. The operation will require 2 passes in 2nd gear. A job efficiency of 0.70 will be used. You need to determine the total time required to complete the work. From the previous example, we know that the forward speed at the 2nd gear is equal 3.4 miles per hour. Applying the equation 5.2, you got the total time is equal to 2 passes multiplied by the distance of 2,000 feet divided by the speed of 3 miles per hour, and 88 is the conversion factor to convert miles per hour to feet per minute. And finally divide it by the efficiency of 70%. We got a total time of 19.1 minutes. When doing finishing or fine grading, production is usually calculated on a square yard per hour basis. The following equation, as shown here, can be used. In this equation, S is the speed of grader in miles per hour. W is the effective width per pass in feet. Don't confuse this with the total width of the blade. The effective width may not be equal to blade width. I will explain this later. E is grader efficiency factor. 5,280 is the unit conversion factor from FT to mile. And 9 is the factor to convert square feet to square yard. Let me explain how the effective width is calculated. This figure here shows a plan view of the grader. This is the total length of the moldboard, and this is the effective width. It is equal to length of blade only when the angle is 0. When the angle gets larger, you got a smaller effective width. Furthermore, the effective width needs to be further reduced due to the overlap between passes. Given a certain position of the blade, with L as its length, and alpha is the moldboard angle, the effective width will be the length of this yellow line. The angle between this yellow and the white lines will be equal to the moldboard angle, alpha. To calculate the effective width LE, you multiply the blade length L by the cosine of alpha. To consider the overlap between passes, you subtract the effective width by the overlap between passes. If the effective width is 10 feet and the overlap is 1 foot, in the first pass, the effective width is still 10 feet with no deduction. In the second pass, due to the overlap, the actual effective width will be decreased to 9 feet. This is the same for the third pass. So, the width of all passes except for the first one will be affected by the overlap. To simplify calculation, we can assume that the reduction is applied to all passes. Caterpillar Performance Handbook gives you a table for quick calculation of the effective width, given the moldboard length and angle. This table is basically based on the equation mentioned earlier. Note that the values in this table exclude the reduction due to the overlap between passes. Let's do another example here. A CAT140M motor grader. with a 12-foot moldboard, is performing road maintenance work. The machine is working at an average speed of 8 miles per hour, with a moldboard angle of 30 degrees. There is 1 foot of blade overlap between passes. If the contractor uses a 50-minute production hour, what is the motor grader's production in square yard of coverage area per hour? To answer this, you can simply apply this equation here to estimate the production. Let's see what we got. We got the speed S of 8 miles per hour. We also got the efficiency of 50 minutes per hour. What is missing is the effective width. As you learned earlier, to calculate it, you need to find the moldboard length, angle, and the overlap width, which are already given. First, to calculate the effective width, you multiply the blade length 12 feet by cosine of 30 degree. You got 10.39 feet. Since the overlap is 1 foot wide, you subtract the effective width by 1 foot. As the result, the final effective width is 9.39 feet. Applying this equation, you can calculate the production. It is 5,280 times the speed of 8 miles per hour times the effective width of 9.39 feet times efficiency of 83%, then divided by 9. The final answer is 36,578 square yard per hour. Section 3. Miscellaneous finishing equipment topics. This is advanced knowledge about automated machine guidance. This part is only for 639 students. Graduate students are required to watch the second video of this chapter. This is the end of this video. Please complete the homework problems at the end of your notes. Goodbye for now, and see you next time.